Hi, we continue with the case in which two nominal variables affect one numerical variable, and we are talking about a within subjects design, and we've seen the parameter estimation approaches, and now we are going to see two model comparison approaches, maximum likelihood and Bayes factors. Okay, so the maximum likelihood is done with R. We've got four models, and these are very similar to the ones we used in the between subjects model comparison, except that now we add the participant dummies. So basically the participant dummies I explained when we analyze the case of one nominal variable affecting one numerical variable and within subjects. So because in within subjects we violate the assumption of independence of observations, because the observations that are contributed by the same participant, they are not independent. So in order to solve that problem, we use participant as a variable, and because participant is a nominal variable, what we need to do is to create dummy variables. But remember that you create one dummy variable less than the number of categories that we have in that nominal variable. So if we have 80 participants, then we create 79 dummy variables. Now that also explains why we don't need to create a dummy variable for the two nominal variables that of interest. We have match and number, and the reason is that they have two values. So if they have two values and we have to create one dummy variable instead of two, then we already have one variable, and so we don't need to create both. We don't need to create anything new. Okay, so basically the model 0 within is the mu's, which are the predictions for each participant, is just one parameter not related to the variables of interest, but we add this vector of gammas and participant dummies, and which are basically the difference between means between participants. Okay, so for model 1 within, they all have the participant dummies, but here is different. The match that we add, and it wasn't there in model 0. In model 2 we add number but not match. In model 3 we add both match and number, and in model 4 we add match, number, and the interaction between the two variables. And these are the parameter, the best estimates for, so they are the estimates that increase the likelihood of the model and reduce the AIC of the model. So we've got a here the parameter values and the AICs. Now I wanted to show you that the R squares are values between 0 and 1, but the adjusted R squares can be negative, and this is because the R square is necessary between 0 and 1, but then the adjusted R square penalizes for using extra parameters, so that penalization can go even below 0. And because we are using a lot of parameters in the within subjects design, because we are creating one dummy variable per participant, so loads of parameters to estimate, then this is possible. But we are interested in comparing using the AIC to compare models, Okay, so basically here model 4 is the best, and that indicates that there is an interaction. So at the beginning, in previous videos, I hinted at the possibility that there would be an interaction, and we confirmed this in the analysis, because model 4, which contains the interaction between the two variables, it's the best model because it has the lowest AIC. Okay, so Bayes factors, we do it obviously with JASP, and we do a repeated measures, Bayesian ANOVA. Let's get the data. So let's go to ANOVA, Bayesian repeated measures ANOVA. And we do the same that we do with the ANOVA. We have to define the repeated measures factors. First one is number, and the levels are low and high. And then we create a second factor, match, and the levels are no and yes. And here we've got RT1, RT2, RT3, RT4. That's it. That's all we need. And then we wait a little bit. And here is the calculation. So basically, we've got model comparison, as I said many times. When we use the Bayes factor, when we compare models to the null model, that is a model comparison, but it's also a testing of the hypothesis that the null model is incorrect. Okay, so basically, when we obtain these, we obtain the Bayes factors here in this column, but we are not reported the Bayes factors that compare the models between themselves. They only compare against the null model. We don't have Bayes factors, but we can use mathematics to do that, and it's very simple mathematics. So, but before doing that, I'm going to show you that it says include subject. So remember that in maximum likelihood we added the dummy variables for participants. Well, here it's done in a different way, but the null model includes the subjects. So this is the Bayes factor table that I showed you in JASP. And now we want to compare the models that are not the null between themselves, and when the two models are compared, so the Bayes factor of two models are obtained comparing to the same model, then mathematically the ratio of those two Bayes factors, it's the Bayes factor between those two models. So we've got we can do that then. Bayes factor of model 2 against model 1 is the same as Bayes factor of model 2 against 0, and divided by Bayes factor of model 1 against 0. So these are the values. Again, if we want to compare 3 and 1, we calculate the Bayes factor 3, 0 divided by the Bayes factor 1, 0, and so on and so forth. So we show that model 2 is worse than model 1. Model 3 is better than model 1, and model 4 is better than model 1. Model 3 better than model 2. Model 4 better than model 2, and model 4 better than model 3 by far. So basically model 4 is better than all the other models. Okay, so now we move to hypothesis testing, and I'm going to show you the NHST approach. And Bayes factor, I'm going to just to indicate that we've done it just now, because comparing against the null is it's a type of model comparison. Okay, so we are going to use JASP, we are going to use ANOVA and repeated measures ANOVA, and we're going to do that now. Okay, so basically this is showing what I've just done, which is the Bayesian repeated measures ANOVA. Now we are going to do the traditional repeated measures ANOVA, so over there. And we have to do this again. We have to put number, low, high, and then another factor is match, no, and yes. So now we put in repeated measure cells RT1, RT2, RT3 and RT4, and that gives us the table for the ANOVA, which is a bit higher. And if when we wanted to do parameter estimation, we said that we were going to explain when we do an NHST. So in the post-hoc test, we put number and match on the other side, and then we get the estimates of the difference between condition low and condition high in the variable number, and the difference in means of the condition no and condition yes in the variable match. Okay, and this is the table that I can show you in the slide. So basically, the variable number, this is the sum of squares. Degrees of freedom is 1, same to match, because it's 1 less than the number of means, and there are 2 means. And an interaction always has a degree of freedom of 1. Now, the sum of squares of the here variable number is the amount of the total variability of the data that is explained by the variability in the variable number. So variability in the variable number is the difference between the 2 means of means for low and high against the grand mean. And so then the residual is the variability within each group. So basically, we are talking about the difference between each individual score and the mean of the condition. Sorry, the mean of the value of the variable number. So, for example, if a individual score is in the condition in which the number is low and there is match, that value will be subtracted from the overall mean of the value low, and any value that involves the condition high, the value high of the variable number, and will be subtracted, so compared to the mean of the variable high, the value high in the variable number. So so basically, when you sum all those, you have to square all those differences, and that is a residual. So because that is not explained by the variable number. So when we calculate the F score, in when we've got more than one nominal variable, the residual, so each main effect or each effect has their own residuals. So you compare the mean square error with this mean square error or residual, and that's the f-score. So for match is the same, is the variability of the data explained by match versus the variability of the individual scores versus the mean to the value of the variable match to which they belong. So when the f-score is calculated by the ratio of the mean square of match and its own residual. Same for the interaction. This is the mean square and these are the residuals. So you can see that the three are quite high f-scores, and so the probability of obtaining these f-scores or higher values if the null hypothesis is true is very, very low. So the decision is to reject the null hypothesis. The last thing I would like to say in this analysis is that these residuals are not considered. So in the between subjects design, there is the residuals, there is only one type of residual, but here we've got as residual the difference between the participants, and that is subtracted from the total amount of residual. So when we do the f-scores, and this is something that is not going to be in the denominator, basically making the scores higher. So that's why within subject designs are very good, because you get rid of a lot of residual that is not going to be incorporated in the calculation, therefore increasing the f-score. Okay, so in terms of the Bayesian hypothesis testing, I've done it already. Basically, I did the ratio of the marginal likelihood of each model versus the null model. Basically, that's the Bayes factor. And when you do a Bayes factor against the null model, that is testing the null hypothesis. Okay, so this finalizes the series of videos about effects of two nominal variables on one numerical variable.